Good morning. My name is Cheryl Olman. I'm an associate professor in the Department of Psychology here at University of Minnesota. I do not identify as a psychologist. I identify as a physicist, and then I did my PhD in neuroscience. And the image I have here is a cartoon of a computational model that we've been working on lately to try to get our head around, even if we could do depth resolved fMRI with unlimited resolution, what would we expect the pattern of neuronal responses to be? In yellow, we have the input to primary visual cortex, and the orange and the red neurons are excitatory neurons. Blue and green represent inhibitory neuronal populations. Purple arrows are indicating feed forward and feedback information coming into this region of cortex. And you can see that with all the connectivity, information so quickly gets mixed between layers that it's often really hard to make predictions about laminar profiles for fMRI responses, even if acquisition and analysis was not limiting what we can do. But today's topics are about acquisition and analysis for doing these depth-resolved fMRI experiments, and we're going to start the two-day workshop with a little bit of a mixer around the different problems we encounter at different points along the way. So the first problem is just the nominal fMRI resolution. How does the hardware limit our ability to get smaller and smaller voxels? Is it signal to noise ratio that's the strongest limit, or what is keeping us from having higher resolution? And then there's the question of the true resolution of our data. And exactly what I mean by true resolution, we'll talk about it for these next couple days. But there's some kind of correlation between our different voxels, and there's spatial correlations that limit the ability to resolve the underlying laminar profiles of neuronal activity. Does this come from the biology and the signal itself that we're measuring, the kind of contrast that we used in our images? Or does this blurring crop up during T2 SWAR blurring for long readouts during acquisition? Or maybe it's the data processing we're doing and we're resampling our data too much, or there's a way we could handle our data processing in order to preserve that nominal resolution that we worked so hard to get. On the anatomical side of things, we're looking for the gray matter to distinguish different neuronal populations that live in the gray matter. But we have resolution limits there also, and we can't exactly see the boundary between the gray matter and the white matter. So what can we do on the acquisition side to maximize the contrast? Improve our resolution, keep the signal to noise ratio high. When we have to do multiple acquisitions, how do we average them together to preserve the resolution of our anatomical images? And then once we have that gorgeous anatomical data, how do we segment it, and how do we use software to draw the boundary of the gray matter and white matter? Do we just all use FreeSurfer, or do we write our own segmentation algorithms? And how do we put that delineation where we need it? And then there's this problem of co-registration. How do we move those gray matter and white matter boundaries into the data space in which our functional data were acquired? Maybe we were so lucky as to acquire a distortion-matched anatomy on which we could do accurate cortical segmentation. That would be the goal, but that's hard to do. And so when we can't do that, how do we co-register our functional and anatomical data? And how does the distortion in this data space of either the functional data, that's where we have the biggest problems, or the gradient nonlinearities that caused warping of our anatomical data? How do we handle that relative distortion, and how do we judge our co-registration when we now have this heterogeneous alignment between our functional data and our anatomical gray matter? And finally, how do we layerify our data? And I'm pretty sure layerify is not a word, but we've got to do something in the voxel-based analysis, a surface-based analysis, or the laminar spatial regression that lets us estimate different fMRI responses at different depths. So that's the exercise we're going to do for the next 15 minutes to get to know each other. We're going to divide into different groups and move around to debate for each thing what is currently the standard approach, what do we just feel like most people are doing, and what are the standard problems that we're encountering. And we're just going to move through each of these topics and have some conversations.